Hello, my name is Wacław Gudowski. I'm professor in neutron and reactor physics at KTH, and I would like to present you our mandatory course in reactor physics, which I am doing together with my very good friend Vasily Arzanov. My symbolic picture on the left-hand side, actually, with magnifying glass, symbolizes a role of reactor physics. It helps us to see how neutrons behave on a microscopic level. So reactor physics is our magnifying glass. What is reactor physics about? Well, it is about physics of the controlled neutron fission chain reaction. It deals with the study and application of neutron chain reaction. It predicts the behavior of the neutron population in a nuclear reactor. It has a prime purpose of efficient energy production and safe operation of nuclear power reactors. What is reactor physics? Well, it is a mature scientific discipline. Basic physical principles are well understood. Nuclear data are measured and evaluated. We deal a lot with the neutron cross-section, as you will see. Computational methodology is developed and validated. And reactor physics is the core subject in nuclear engineering. This course is an obligatory and very important course in the master program in nuclear energy engineering. What is the focus of reactor physics? Neutron sources and neutron detectors, cross-section of neutron interactions with matter, transport of neutrons, mostly in diffusion approximation, but not only, fission processes and fission chain reactions, concept of criticality and reactivity, and finally, how to keep this chain reaction under control using delayed neutrons and understanding their role. Focus of reactor physics is also temperature feedbacks, how to keep reactors safely under control, and how to design a nuclear reactors. Code for nuclear reactor simulations, both deterministic and statistical, so-called Monte Carlo methods. An insight to spent nuclear fuel and nuclear waste management will be given also, presenting, for example, new ideas of accelerator-driven system. Here you have the artistic vision of the transmutation system, a complex of proton cyclotrons with cooling system, which you will see. This is a cyclotron. This is a first step of the cyclotron. This is an artistic vision of the cooling system, as you will see. All the piping, cooling here, and here we have an electrical generators, assuming that we will produce also electricity with the transmutation system. And if for the moment we put ourselves on the proton, on the microscopic level, we will see the mechanism of the spallation process, which is actually a very, very strong neutron source, which we can use for transmutation purposes. There will be a bonus of studying reactor physics. A historical survey of the milestones of nuclear physics since about beginning of the 20th century is given as an introduction to that lectures. Here you can see myself visiting the first fast reactor producing electricity, only for one bulb, by the way, at that time. That was 1951. And here actually I am running the first commercial nuclear power plant delivering district heat to the city of Obninsk in Russia. The course gives also some practical understanding of reactor operation through laboratory exercises conducted either at the departmental reactor simulator and at the research reactor ISIS in Saclay in France. This is a cross-section of the ISIS reactor in Saclay. Having finished the reactor physics course, you will be able describe and characterize and evaluate neutron interaction with matter. You will be able to describe neutron fields in media, understand the fission mechanism, describe and evaluate neutron slowing down processes, derive and solve, important to solve equation of neutron transport in multiplying media, understanding the very important role of delayed neutrons, understanding temperature feedback, reactor kinetics and reactor dynamics, and then you will be able to evaluate important reactor parameters, including performance and safety. Last but not least, having finished the reactor physics course, you will be able to distinguish between sense and nonsense in nuclear technology, and hopefully in physics, without using such a drastic method as illustrated by Hieronymus Bosch on his painting called Treating of Stupidity. If any question, contact us, either myself, Wacław at KTH SE, or Vasily Arzanov, Arzanov at KTH SE. And remember, we fly high. Thank you very much.